Hey everyone, today I'll be talking to you about optogenetic modulation of cardiac membrane potential as an antiarrhythmic therapy. So, as you might know, the heart is an electrically driven pump where electrical activity results in mechanical contraction. Disturbances in the heart's electrical activity can be deadly. These are commonly known as arrhythmias. Arrhythmias are caused by electrical activity not reaching a resting state after electrical excitation occurs. Researchers are exploring something called optogenetics as a new way to stop arrhythmias. So what's optogenetics? Well, optogenetics refers to the use of light and light-activated ion channels to modulate electrical activity in the heart. My goal is to use optogenetics to stop arrhythmias by aiding electrical activity in achieving a resting state. My first aim is to understand my optogenetic tools and how they affect the heart's electrical activity. My second aim is to establish an arrhythmia model. And then in my third aim, I will use optogenetic tools to stop arrhythmias. So now my methods. We are interested in two specific optogenetic tools, an anion selective light activated channel called ACR1 and a cation non-selective channel called CHR2. Turning your focus to my schematics in the methodology section in the right, you can see that activation of ACR1 by green light causes chloride to flow across the cell membrane, while activation by blue light for CHR2 causes sodium or calcium to flow across the cell membrane. This ion flow is actually what causes the modulation of the heart's electrical activity. It actually modulates the cellular membrane potential. I just want to briefly say that the change in membrane potential is characterized by a waveform known as an action potential. How these waveforms change due to activation of ACR1 or CHR2 can be in the schematics, again in the top right in the methodology section. Further right to these schematics is my experimental setup, where experiments were performed in whole heart adult zebrafish expressing ACR1 or CHR2. I measured action potentials by using sharp electrodes, and I activated ACR1 or CHR2 by green or blue light through a fiber optic cannula that is focused on the heart. Arrhythmias were then induced by pharmacological activation of calcium current and block of potassium current, currents that are both important for electrical activity to reach a resting state. So now, jumping into my results, I'll begin with aim 1 and understanding the effects of our optogenetic tools. So the waveforms that I was talking about, action potentials, are seen in the bottom left corner in figures 1 and 3 again. These figures depict how ACR1 or CHR2 activation by sustained green or blue light modulates the action potential with varying light intensity. Membrane potential is on the y-axis and time is on the x-axis of these figures. In the figure legends of each of these is their respective light intensities, where control is seen in black and each light intensity step is the increase in the luminescence of light, reaching a maximum blue or a maximum green. Below these figures in figures 2 and 4 is the analysis on the change of action potential parameters with increasing light. We found similar changes due to activation of ACR1 and CHR2, but for the sake of time, I turn your focus to the graphs outlined in black. These graphs depict how action potential duration changes due to the increasing light intensity. Recall when I said that arrhythmias are caused by failure of electrical activity to reach a resting state. We have shown in these specific graphs that ACR1 activation aids membrane potential in reaching a resting state faster, while CHR2 does not, suggesting that ACR1 may be used as an antiarrhythmic tool. Moving on to aim 2, the middle of the poster in figure 5, we found that pharmacological manipulation of the ion currents that I previously spoke about caused arrhythmias in the whole heart. You can visualize how the electrical activity of the action potential fails to reach a resting state as the drugs incubate over time, resulting in very long action potentials when comparing it to the control. So now we have understood our optogenetic tools, selected ACR1 as our antiarrhythmic tool because it can repolarize or reach an resting state faster for the electrical activity, and we established our whole heart arrhythmia model. Can we successfully suppress the arrhythmia by activating ACR1? Lo and behold, it actually worked. In figure 6 in the middle, I was able to induce an arrhythmia as seen in the red action potential, and then by activating ACR1 with sustained light, I'm able to aid the electrical activity in reaching a resting state faster. But you can see that the shape of the action potential is not really similar to control. So I also tried timed activation, and it also worked. So it all really works. So what do I want you guys to leave here with and tell your friends about? Well, arrhythmias are deadly disturbances of the heart's electrical activity. Optogenetics can change the heart's electrical activity by activating channels with light. And here I've shown the feasibility of using optogenetics to stop arrhythmias. As far as where my research is going, I'm now using dye-based fluorescence imaging to understand what is occurring on the whole heart and what these arrhythmias are doing, and to allow for spatial targeting of light application. Although it's a small figure in the bottom there in the conclusion, I believe that this is important to show because these presentations are really about sharing ideas. And optogenetic activation and fluorescence imaging has not been optimized in previous literature, and maybe someone here can use this idea as my setup allows for this. That's all. Thank you, and I'm happy to take any questions.
Thank you. Dr. Gutierrez, do you have any questions? I think you're muted right now.
Okay. So do you see any technical risk associated by integrating a light activation on the heart?
Practical risk?
Technical risk.
No, I mean, I've shown, and the previous literature has shown that like shining a light on the heart, people have shown that you can silence activity, modulate activity, and as soon as the light turns off, it can go back to regular activation and regular excitation in the heart.
Now, do you see that this could be an implantable device or?
Oh, it's for its clinical relevance. Yeah. I mean, honestly, I know it really sounds all like science fiction and like stopping arrhythmias with lights and stuff, but a lot of research depends on transfection of channels in humans, honestly, and well, specifically optogenetics does. And if it's capable, and we've shown this happens in a zebrafish, and we can do it in mammals, then I really think that we can do it in humans. And imagine like an implantable cardioverter defibrillator. Instead of a high voltage shock, you get a light turned on, and it stops the arrhythmia and puts it back into normal rhythm. So I think it's possible. Instead of a voltage shock, you get an LED turned on. And they actually, there is literature showing that they did this in pigs, where they put a fiber optic cannula inside the pig heart. So I think it's possible.
Thank you. Dr. Bai, do you have any questions?
Yeah, so one question is like, have you thought about trying to use the, further modified, receptor, to achieve, so that the ion channel can be activated through different wavelengths, for example, like far red, so that you have better, penetration of the signals. Yeah.
So that's the cool thing about optogenetics. There's a whole optogenetic toolbox where each channel or light activated channel is activated by specific wavelength. So ACR1 is only excited by 530 nanometers. CHR2 is excited by 470 nanometers. There's deeper penetrating lights, like you said, the red ones. I don't think there's a chloride one that is excited by red light. There is a CHR2 one, but from my experiments, deeper penetration for sure is relevant in humans and mammals, but the zebrafish, 470 nanometers and 530 nanometers is plenty to go right through the tissue.
Cool.
All right, thanks, Ahmed.